Okay, so it is a good time to talk about algebra because we are going to talk about discrete logarithm problem, but discrete logarithm problem actually depends on the algebraic group that we are going to work on. So in order to understand the hardness of the discrete logarithm problem, we have to see a little bit algebra. Basically, we need to know what a group is, a ring is, and a finite field is, okay? So we will go in that order. So let's start with a group. A group G in algebra is a set of elements together with a binary operation. You can choose any notation you want. I use star here. So this binary operation is on G, okay? That combines two elements in G and form a third element in G, satisfying the following group axioms. One is associativity. So regardless of where the parentheses are, these two operations has to be identical. Similarly, the next axiom is identity element. We want an element E such that A operation E should be equal to E operation A, which should give you A. So E is the identity element here. Finally, inverse element. Every element has an inverse. This is the axiom. So if it doesn't, then we don't tell it group. But the definition of an inverse is as follows. So B is inverse of A if A operation B or B operation A gives you the identity element of this group. Okay. So let's say an example. Of course, this is probably the basic example you had in mind. Think about integers and the addition operation. So there's associativity, right? I don't care where the parentheses are, the results will be identical because we are simply adding stuff. So if you have doubts, just do it. Identity element 0 in addition, right? This is the first thing they teach us in elementary school in mathematics, you know. So A plus 0 or 0 plus A gives you A, regardless of which A you are using. And every element has an inverse here, because if you give me an A, I will tell you that minus A is the inverse of it, because if you add A to minus A, you end up with 0 identity element. So this is a group, okay? Z star with multiplication is not a group. By Z star, we are talking about Z minus the 0 element, okay? So you're removing the 0 element, and generally we represent it with Z star. And if you think about multiplication operation, this is not a group. So yes, it satisfies associativity regardless of where the parentheses are. These multiplications are identical. There's an identity element, which is 1. So multiply any element with 1 in Z star, it will give you itself. This is why we actually remove 0, by the way, because 0 multiplied with 1 wouldn't give you 1, okay? But the problem is that not every element has an inverse. Actually, only one has an inverse. Because think about it. If you give me A, I need something like 1 over A so that I can multiply both of them and end up with 1, right? But 1 over A is not in Z star if A is different than 1, right? Think about 3. 3 doesn't have an inverse here. I cannot multiply 3 with an integer and end up with 1. So this is not a group. So as you can see, since this is the main problem here, if I focus on rational numbers, then this becomes a group, right? Because now 1 over A is a rational number, so it is in this set, so it satisfies these axioms. So since we are going to represent digital data as group elements, we mostly focus on finite groups in cryptography instead of infinite groups. Because if you focus on infinite groups, you know, for instance, if you want to encrypt something, your data might be a few kilobytes, but after encryption, it might be petabytes, right? I have to keep this space to finite. So this is why generally we deal with Zi, let's say. So for instance, Z4 here is the group where Z4 is 0, 1, 2, 3. And with addition, this is again a group because you have the associativity now modulo 4. Identity element is still 0. And every element has an inverse. For instance, 0 plus 0 is 0. So 0 is the inverse of itself. 1 plus 3 is 0 modulo 4. So 3 is the inverse of 1. And also 1 is the inverse of 3, as you can see. And 2 is the inverse of itself because 2 plus 2 is 0 modulo 4. So as you can see now, the inverse element is a little bit different than the infinite groups I gave as an example, right? So this is a little bit counterintuitive, but 1 is the inverse of 3 and 3 is the inverse of 1. in this group, of course. Again, Z4 star, this is a finite set, but it's not a group. So by Z4 star, we are talking about elements 1, 2, 3. And here the problem is that not every element has an inverse. For instance, 2 doesn't have an inverse because I'm here multiplying 2 with every element in this set. For instance, 2 plus 1 is 2, 2 plus 2 is 0, and 2 plus 3 is 2. So none of them gave me the identity element, which is 1 in the multiplication, right? So Z4 star is not a group. 2 has no inverse in Z4 star because actually the greatest common divisor of 2 and 4 is not equal to 1. So they are not relatively prime. This is why I chose 2 as an example, and I didn't end up with an identity inverse element. First, 3 has an inverse element here. Multiply 3 with 3, you will end up with 9, but it equals to 1 modulo 4. So 3 is the inverse of itself here. But not every element has an inverse like 2. So as you can see, if this is the deal breaker, if I choose a prime number instead of 4, since all of these numbers are less than that value, they have to be relatively prime. In other words, if you choose that P star, as the group operation, I choose multiplication, and P here is a prime number. So that P star is just the elements starting from 1 to 3 to P minus 1. Now, again, it satisfies associativity. 1 is the identity element, but now every element has an inverse because greatest common divisor of A with P would be equal to 1. Okay, of course I have to prove it, but I'm just telling you, you can use number theoretical arguments to show that this is the case. Okay, so this is why generally we deal with prime numbers in terms of group elements or field sizes and so. Okay, so ZP star is something you should be familiar with. Let's talk about a generator of a group. Small g here is called the generator of the group G if every other element of the group may be obtained by repeatedly applying the group operation to G. Okay, so from a single element, you generate all of the other elements. Each element can be written as a power of G in multiplicative notation. Each element can be written as a multiple of G in additive notation. This is generally what we do when we deal with groups, rings, and fields. So let me show you an example. 2 is not a generator of Z7 star with respect to multiplication. Why? Because take the first power of 2, it is 2 modulo 7. Second power is 4 modulo 7. Third power is 1. So I end up with the identity element. So I stop here because if I take the fourth power of 2, I will end up with 2, 4, 1. So this is going to repeat itself, right? But I could only generate 3 elements from 2. But as you can guess, Z7 has 6 elements, so I couldn't generate all of them. So 2 is not a generator of this group. But what about 3? I claim that this is the generator because calculate every power of 3, you end up with having all of the 6 elements of Z7 star. So in this scenario, actually what we call that 2 has an order of 3 because it generates 3 elements. 3 has an order of 6 because it generates 6 elements. So this is not a coincidence that 3 can divide 6, by the way. If your group, in our scenario, the group is Z7 star, so it itself has 6 elements, so its order is 6. So any element that we use as to generate some stuff, it's going to generate number of elements that can divide 6. So this is no surprise that this is 3. Okay, but not that important. Okay, this is coming from group theory, so just if you're interested, go and look at the formulas or theorems. So more algebra. In order to explain rings and fields, I have to go with this. So let's talk about abelian groups. A group G is said to be abelian if X operation Y is always equal to Y operation X for every XY in this group G. So you might say that, isn't this the case all the time? You might get that intuition because I always talk about addition, multiplication. So these are commutative. So this is why you feel like this should be always the case. But think about matrix multiplication as your star operation. So it is not commutative actually. Multiply two matrices, X and Y, then multiply Y and X. Most of the time you will get different results, okay? So this will lead us to the definition of ring. A ring R in algebra is a set of elements together with two binary operations. In the group we had one binary operation. Here we have two operations, plus and multiplication, let's say, on R satisfying R is an abelian group under addition. So this is what we have seen so far in groups. So I want R to be a group under addition, but also it should satisfy some properties with respect to the second operation. Here I represented with star, you can call it a multiplication, but it should satisfy associativity like this. Also, it should have distributive properties with respect to these two operations, like A star B plus C, where B plus C is in parentheses, will end up with A star B plus A star C. So think about multiplication of a, addition. This is what we do in multiplication, right? So if you have such a set with these two binary operations satisfying these operations, then we call this set is a ring under these operations, okay? Here are some examples. Zn with respect to plus and multiplication, or Z with respect to plus and multiplication are rings. But the important thing is that with respect to multiplication, don't forget that these sets doesn't have inverses. So they are not also grouped with respect to multiplication. But as you can see, the definition does not force me to have multiplicative inverses. This is why I can tell them these are rings. Okay, but they will not be fields. This is what I'm going to talk. A field is something more. A field is a set F which is closed under two binary operations plus and multiplication. Closed under two binary operation means that take two elements, apply that operation, the result is still inside that set. Okay. So now I force it to be, so this is something more than a ring, because now I want F to be an abelian group under addition, but I also want F star where I remove the zero element, and I want it to be an abelian group under multiplication. So it will be grouped under two operations. Here's an example, ZP with respect to addition and multiplication. This is a field when P is prime, and generally we use this notation FP. Electronics engineering people generally refer to as GFP, saying that this is Galois field. And it is, but it is just a matter of test. So mathematicians prefer to use this notation. So finite fields. If Q is a prime power, then there's essentially only one finite field of order Q, which is denoted by FQ. So this means that, by choosing these operations or sets, I can create different finite fields. For instance, a question is, can I create a finite field with 6 elements? The answer is no, because 6 is not a prime, but also is not a prime power. By prime power, we are talking about any power of a prime number, like 3 to the power 8, okay? Or 3 to the power 10, or 2 to the power 10, which is 1024. This means that you can create a field with 1024 elements, but not a field with 6 elements. So choose any 6 elements, define any 2 operations. It won't be a group under both of them. That is what I'm claiming. So these are important. This is why generally we will be trying to find huge primes to create such a field and work on them in many areas of cryptography.